Welcome. So far we built a cluster and secured it. Now it's time for the main event, running our application. In Kubernetes, the objects that run your application are called workloads. While there are many types of workload for different use cases, like stateful sets for database or jobs for batch processing, the foundation for most application and the core focus on Kubernetes rests on three key resources: the pod, replica set, and the deployment. Let's start with the most fundamental unit of all, the pod. A pod is the smallest deployable unit in Kubernetes, and it's where our replication container live. We could simply create a single pod to run our application, but this is a terrible idea in real world. Why? Because it's a single point of failure. If a pod crashes or a node it's running in or fail, our application is down. There is nothing to automatically restart it. It doesn't self-heal. To solve this problem, we need a higher level of controller. This brings us to ReplicaSet. ReplicaSet is a primary job to ensure that the specific number of identical pod or replicas are always running. If a pod dies, the ReplicaSet controller immediately notices and create a new one to take its place. This gives us the self-healing and basic scaling we need. But in modern Kubernetes, we rarely ever create a replica set directly. Instead, we use even more powerful controller that manage replica set for us: deployment. Deployment is a workload resource that will use 90% of time for your stateless application. It does everything a replica set can do, ensuring your desired number of pods are running, but it adds a critical feature on top: the ability to manage declarative update to your application, allowing for seamless rollout and rollback. You don't manage replica set. The deployment does it for you. When you want to update your application, you tell the deployment and it handles the entire process by creating a new replica set and carefully manage the transition. Let's see in action. We can create a deployment imperatively using kubectl create deployment command. Let's create a deployment named app_memcache using app_memcached image, and we will ask for 4 replica. Let's first delete the existing app_memcache and then create the deployment app_memcache with image 1.6.8 and replicas 4. As you can see, it's created. While the imperative command is quick, the standard way for managing Kubernetes objects is declaratively using YAML file. Let's look at the manifest of deployment we just created. To see the deployment, I'm going to use get deployment, and then I'll get the deployment, and then I'll use -o YAML. -o means output, and then we want to get the output in YAML format. Let's break this down. Spec replicas is simple. Our desired state is 4 pod. A spec template is the most important part. This is the exact blueprint the pods that deployment will create. Everything inside the template section is standard pod specification. Here in the template section, we have spec and the container like image version and then mount points and volumes, and we can add to the pod. And finally, the glue that holds together a spec selector. As you can see, we have selector here, app_memcached, and here in the selector, we are going to use this label. The deployment uses this label selectors to know which pod is supposed to manage. The match label in the selector must exactly match the labels defined in the pod template. Ensure that each replica set has a unique label selector within the namespace to avoid conflicts. A pod can only have one owner. For a replica set to manage a pod, the pod must properly labeled and not already owned by another controller. This can result in unpredictable behavior, such as controller failing to manage pod correctly or even deleting pod that another controller is responsible for. Let's inspect the objects that we created. We see that our deployment and the result of all 4 replicas are ready and available. If we get these pods and replicas, we can see the full picture. As you can see, we have 1 replica here. The desired is 4, and the current pods running are 4, and it's the age is 2 minutes. If we delete the deployment, the entire hierarchy is automatically cleaned up for us. This is called cascading deletion. Let me remove this. And everything is gone. So you can see that the only remaining pod is Ubuntu, which I created 20 hours ago, and it's standalone. Okay, rolling updates and rollback. The self-healing and management is great, but the real power of deployments comes from managing application lifecycle. Let's say we need to update our Memcached application from version 1.6.8 to 1.6.39, the latest version. Let's create the deployment again, and this time we are manually annotating the deployment for keeping the version. So here I'm going to use create deployment command again. So the deployment created, and now I'm gonna annotate the deployment with app memcached. So here I'm using this annotation, Kubernetes IO change cause. This keep the history for us. Let's check the history before annotating the deployment. Let's check the history of deployment. This history command shows us the current version of our deployment. As you can see, the change cause is none, which means that we don't have any idea what happened on this version. But if we manually annotate the deployment, then we can keep track of history. This is recommended because this can be helpful when you want to do the rollback or checking the history. So right now I'm annotating the deployment with initial version using 1.6 image. And then when I'm checking the history again, I have this 1.6 image as a history. The kubectl get pods command by default doesn't show me the image. So right now, if I'm run this command, it shows me that the pod and status and the restart and the age. But I'm going to use custom column. I'm again using the O command instead of YAML. Now I'm going to use the custom column. And the custom column, I'm going to use image, node, and status. So as you can see, these 4 pods are running on my worker node, and they are all using the Memcache version 1.68 image. Now for update image, we can declaratively tell Kubernetes our new desired state using the kubectl set command, set image command. So I'm going to use this command, and here, as you can see, the image version is 1.6.39, and I'm using this record flag. As you can see, flag record has been deprecated. Record will be removed in the future. So I've added record flag. This is a great habit. It saves the command we just ran in the deployment history, which is useful for auditing later. The future is going to deprecate. So you can annotate if the record got removed from the kubectl. So let me check the history again. You can see that the second history has the kubectl get set deployment app memcache with the 1.6.39, and we have this dash record through here. So this recorded my command. If I've done this without the record, it was empty because you couldn't see what happened. Know what's happening behind the scene? The deployment has created brand new replica set with updated container image. It is new carefully terminated all pods and creating a new one in control way to ensure that there is no downtime. This is rolling update. We can watch the status of this process in real time. So if you check the status of deployment, it's successfully rolled out. We'll see that initial creation as reversion 1 and our update as reversion 2, which is this. Because we use the record flag, the change cause column tells us exactly what we did. But what if our new version 1.639 has a critical bug? We need to revert it to the previous version fast. This is incredibly easy with deployment. So if we undo the deployment, app memcache will be undo. So if we get the column again, we can see that it's going to roll back to 1.68. As you can see, one container remained. And then if I get again, yeah, this all rolled back to the previous version. That's it. By running rollout undo, we'll tell the deployment to go back to the previous reversion. Behind the scene, it performs another rolling update, scaling down the bad replica set and scaling the old, stable one backup. If you check the history again, you'll see that Kubernetes has intelligently managed the reversion. Okay, as you can see, it's 2, and the 3 version is initial version. And this is happening like ongoing if I do the undo again. So to recap, pods are the basic units that run our container. Replica sets ensure a stable number of pods are always running, providing a self-healing. And deployment manage replica sets to give us a powerful zero-downtime application lifecycle feature of rolling update and rollbacks. For any stateless application you run on your Kubernetes, the deployment will be your go-to workload resources. It's a declarative, self-healing, and robust way to manage your application. In our next topic, we explore how to update and scale these workloads.